Alright, so we've explained that chi-squared is used when you are wanting to perform inference on categorical variables, and we have already seen one example of the chi-squared goodness of fit test. Here we're going to do just another example of what goodness of fit is and what it looks like. So here we're looking at some data about births in a hospital, and what we want to know is, are births evenly distributed across the days of the week? So we have this table, and it tells you how many babies were born on each day of the week. This is from a sample of 140 birth records. And I want to know, do these data here give us evidence to show that local births are not equally likely on all days of the week? So think about your null hypothesis. When we've written null hypotheses in the past, we always use an equal sign. Well, equal means same. So your null hypothesis is that births are equally likely on all days of the week. It's the same on Monday as it is on Tuesday, as it is on Wednesday, as it is on Thursday, as it is on Friday, and Saturday, and Sunday. Right? But our alternative hypothesis is that the breakdown is different. We're trying to prove here that births are not equally likely on all days of the week. So let's go through our formula. So we have here what we observed, but remember the chi-squared formula. We need to do the sum of the observed minus expected squared over expected. So we have the observed data. That's what you actually collect from your sample, but you need to calculate the expected. So the expected is based on whatever your null hypothesis is. Here our null hypothesis is that the births are equally likely. And if I add these up, I think it told me before, but I'm just going to double check. It said that there were 140 births total. If you have 140 births split evenly over 7 days, you're just going to do 140 divided by 7. So it should be 20, 20, 20 all the way across. If it was exactly equally distributed, it'd be 20 all the way across. Now here we can see that it's not exactly 20 all the way across. But we want to know if these differences are significant enough for us to say that births are not equally likely, or could this just be a coincidence? Okay, so what we're going to do is we're going to run through the chi-squared formula. So I'm going to take what I observed minus what I expected squared over the expected. So here that would be 13 minus 20 squared over 20. This is 2.45. For Monday, we observed 23. We expected 20 births over 20. It's given me 0.45. On Tuesday, I'm going to take my observed value minus my expected value over my expected value. Just 0.8. On Wednesday, I take my observed value minus my expected value over my expected value. Here I get a chi-squared value of 0. That's because there is no difference between what we observed and what we expected. Thursday, 27 minus 20 squared over 20. This one's also going to be 2.45. On Friday, we've got 18 minus 20 squared over 20, which is 0.2. And on Saturday, we've got 15 minus 20 squared over 20, which is 1.25. So we can get our test statistic here. All of these numbers are based on our data. So to get our total chi-squared value, we're just going to go through and add those together. And I'm getting 7.6 for that test statistic. So the test statistic is based on the test that you ran. The data that you collected is your test statistic. Now what we need to do with that is compare it to our critical value. So critical value is the one that you go look up on the chart, and it's based on degrees of freedom. Here we have 7 days of the week, so our degrees of freedom, 7 minus 1, would be 6 degrees of freedom. And we're just going to use a significance level of 0.05. That's just what we commonly use in this course. So I'm going to look on my chart, 0.05, 7 degrees of freedom is 14.07. Now, picture what that looks like. If I draw a little chi-squared graph up here at the top, remember chi-squared is right skewed. The start of the curve over here is at 0. So the 14.07, your critical value, if I draw 14.07 on here, that tells me that from here down is a probability of exactly 0.05. So from right here onward is exactly 0.05. Well, my test statistic is 7.6. That's like somewhere in this region. So it is not in the shaded area. In fact, from 7.6 down would be a probability much higher than 0.05. So in this case, it's not in that shaded region. So our conclusion is that we would fail to reject the null hypothesis. And remember that your null hypothesis was that births are equally likely on each day of the week. And our alternative was births are not equally likely for each day of the week. So here, if you fail to reject the null hypothesis, this thing that we were trying to prove, it just means if you fail to reject, it just means you don't have enough evidence to prove this. Because that is what you were trying to indicate, was that births are not equally likely. So when you don't reject the null hypothesis, all that means is you can't prove what it is that you were trying to prove. So we say there is not enough evidence to conclude that births are not equally likely on all the days of the week.